Thanks, Matt, and thanks to all of you for coming. I'd like to tell you a story today about a wayward piece of oceanographic instrumentation that wandered into a part of the ocean that we've never measured before, and what it has told us about the vulnerability of the Antarctic ice sheet. I'll start with this photo, which is of an ice shelf. You've heard about ice shelves a bit today, but I'm not sure you've seen a picture of one. The vast amount of ice that sits on the Antarctic continent is always moving, and it's spreading from the center out to the edges, more or less. When it gets to the edge, when it gets to the ocean, it starts to float. And that floating part of the Antarctic ice sheet is what we call an ice shelf. And they're important, as you've heard, because they act to hold the rest of the ice on Antarctica. They buttress the ice sheet. They provide some resistance to that flow from inland Antarctica out to the sea. And as Paul I will also try to, in my talk, pull together a few of the threads that have been mentioned by the two Pauls and Taz and Philip and possibly others. So Antarctica is obviously covered with a lot of ice. That, you can think of it a little bit like if you took the continent of Australia and covered it with 3 or 3.5 kilometers of ice, that's something like the volume of ice we're talking about, a bit more than that. That 58 meters that Paul mentioned, as he said, is not anything that's likely to reach the ocean and raise sea level in the near term. Some parts of the ice sheet are more vulnerable than other parts. And in particular, if you take all the ice off of Antarctica, what you're left with is this. The greenish and orange colors here are bits of the Antarctic continent that are above present-day sea level. Everything shown in blue is below present-day sea level. A lot of the ice is sitting on that blue bit, about 22 meters altogether. And that's the part of the Antarctic ice sheet that is potentially most vulnerable and most prone to being lost and therefore raising sea level. About 3.4 meters of that so-called marine-based ice or vulnerable ice is in West Antarctica that we have generally focused on in past decades when we think about Antarctic ice sheet and its contribution to sea level. But there's much more marine-based ice in East Antarctica. And so we only have to lose a small amount of that East Antarctic ice to have an impact on global sea level that's comparable to what might come out of a larger, more rapid loss in West Antarctica. Let's see if I can get this to play. There we go. When Antarctica loses mass, when meltwater from Antarctica reaches the ocean, it does more than just increase the sea level. It does more than raise sea level. As Paul Spence mentioned, let's play it again because, oops, if I can. There we go. What I'm showing here is a numerical model simulation where we take as you've heard about, the best model in the world for simulating Southern Ocean processes and circulation. Add meltwater from the Antarctic, melt from the Antarctic ice sheet and see what happens to the ocean. And what happens is that the deep ocean warms. And so the plot on the left here shows how the warming of the deep ocean up to 2050. And you can see that the basins around Antarctica are red. They're warming rapidly. The plot on the right is the sinking around Antarctica and the overturning circulation that's driven by that. And Paul showed an example, a movie of how that dense water is formed around Antarctica and sinks into the deep ocean. That drives an overturning circulation, which is largely responsible for the ocean's ability to take up and store heat and carbon dioxide and thereby regulate climate. So this overturning circulation were to slow, we're concerned about that because there's a potential positive feedback where the slower that overturning circulation goes, the less carbon and heat the ocean takes up, and therefore the more rapidly climate changes. And we know from observations that this deep overturning, Antarctic overturning circulation has already slowed by about 30%. And the graph on the right here shows how as we add meltwater, it makes the waters around Antarctica lighter and lighter, more buoyant. That eventually gets to the point where it slows down the sinking around the edge of Antarctica and this whole overturning circulation slows down. In this model simulation by about 40% by 2050. and continuing to decrease. We've also heard about how the fate of the Antarctic ice sheet depends on the surrounding ocean. So where the ice flows off and forms these floating ice shelves, the ice is exposed to the water below the ice shelf, at the base of the ice shelf. And what this graph shows, the red colors on the map of Antarctica are where that's the thinning rate of Antarctica, how much the ice is thinning or where the Antarctic ice sheet is losing mass. In the ocean around it, it's the ocean temperature where red is warm and blue is cold. And you can more or less pick out that where the warm ocean waters get up close to the edge of Antarctica, that's where Antarctica is losing the most mass. So the ice shelves and the ocean interaction with the ice shelves are one of the important things that we need to know about if we're going to anticipate just how fast and how much sea level is going to rise. So this illustrates how the water gets in under the ice shelf. The red arrow here is representing warm ocean water spreading from offshore up onto the continental shelf of Antarctica and then under this floating ice shelf. Once it gets there, it melts the ice from below. And the meltwater is depicted here as a blue arrow rising up under the ice shelf and then heading off in the upper part of the ocean. What's also included on this particular depiction of this process is a bump in the seafloor, a little ridge on the Antarctic continental shelf. And that's important for the story I'm getting to today, because the shape of the seafloor on the Antarctic continental shelf regulates how much of the ocean heat offshore can actually get to the ice. So I'll come back to that in a minute. So I've said that the fate of the ice sheet depends on the surrounding ocean, and in particular on how much ocean heat gets to the base of the floating ice shelves. So what we really need to know is how much heat gets there, how much heat gets to the cavities below the Antarctic ice shelves. Unfortunately, that's about the most difficult part of the deep ocean, to reach. It's covered by hundreds or thousands of meters of ice. These ice shelves, as both Pauls mentioned, are vast volumes of ice that extend deep into the water. So one thing we can do if we have a fancy enough unmanned submarine is send that under the ice shelf, and it can take measurements of the temperature, the salinity, and the bottom depth. And that's been done in a handful of locations so far around Antarctica. It's a big exercise, it's tricky, and it's risky. Several of these many multi-million-dollar instruments have been lost under ice shelves. It's a high risk, high return sort of activity. It's one thing we need to do. We can also drill a hole through the ice. It's hundreds or thousands of meters deep, but we can drill a hole with a hot water drill, basically melt the snow and ice, and then pour it through this drill rig, which melts its way down through the ice shelf. And that leaves a hole that we can lower instruments through. The picture on the upper left is a US instrument called IceFin. It's attached to a tether. So you lower that down through the hundreds or thousands of meters below an ice shelf. It swims around below the ice shelf, collecting measurements, and then you can reel it back in with the tether. What's more common is the picture on the lower left, which shows an Australian team drilling a hole through the Denman glacier to collect measurements of the ocean beneath. All of these approaches to measuring this critical region below the floating Antarctic ice shelf is hard. It's costly. It's a huge logistic exercise to get lots of people deep into the field. It takes a long time to melt the hole. Even once you've melted the hole, sometimes it doesn't work out so well. Those of you who've followed the news from the Thwaites operation that Paul mentioned in the US and UK, drilled a lovely hole, collected a few measurements, were about to deploy the thing they really wanted to deploy, and it got stuck in the hole. And it was time to go. They had to leave because the winter was coming on. So it's a tough exercise. What if there was another way? And the other way involves something called a profiling float. And there's a model of one in the other room, and that one is a clear cylinder. The profiling float, it's a cheap, simple instrument that measures temperature and salinity and pressure. And from the pressure, water pressure, we get the depth. And it can do two other things that make it particularly useful. One is it can communicate to satellite. So in the upper picture here, you can see a black stick coming out of the float. That's the antenna that allows the float to talk to the satellite. That allows the float to send data back, but also to get a position from GPS satellites. The other thing it can do is change its buoyancy. So it's got a pump inside and an external bladder. If it pumps oil into that bladder and makes the float a little bigger, that makes the float buoyant and it can rise to the surface. Transmits its data and then deflates the bladder. That makes it less buoyant and it sinks back down again and drifts with the ocean currents. We can't steer them, but sometimes they drift into areas that are particularly useful for us. So what I'd like to tell you about today is a profiling float that collected some observations near and beneath the Denman Glacier and the adjacent Shackleton ice shelf. So in this picture, there's a river of ice flowing from the bottom of the image out into the ocean in the top of the image. This single glacier holds enough ice to raise sea level by 1.5 meters. That's about half of all of West Antarctica, for example, of the marine-based ice in West Antarctica, and a substantial fraction of Greenland. So it's a big system, and we care if it is to start melting more rapidly and losing mass more rapidly because it could have a big impact on sea level. It feeds into and is adjacent to something called the Shackleton ice shelf. So we deployed a float actually somewhere totally different, the Totten Glacier. And after about 3 months, that, much to our dismay, that float left that area and went into the open ocean. It was disappointing because where we really wanted to be was measuring how much warm water got under the Totten ice shelf. But it popped back up again near the Denman, which is shown by the green dot in the upper right of this picture, and then spent another 2 years in this area, including 8 months beneath the Denman and Shackleton ice shelves. And before going to tell you what what we learned from the float, it's worth thinking about it. It spent 8 months under this ice shelf. It wasn't designed for this. It's saying, what have you done to me? I'm not supposed to be here. Every 5 days, it tried to get to its resting depth of 1,000 or 2,000 meters, but it kept hitting the seafloor and stopping. We'd try to rise and it would run into the base of this ice at 100 or 200, 300, 400 meters deep, saying, this is not what I signed up for. This was not it. And then doing it again every 5 days for 8 months. It's amazing that it survived, and serendipity, one of the lessons from this story is that there is some serendipity in science. We designed this mission so that the float could do its best job of surviving in this hostile environment on the Antarctic continental shelf, but we didn't put it under these ice shelves. We didn't steer it there. The ocean currents happened to carry it there. The measurements made by this float are the longest transect under an ice shelf we've collected anywhere in Antarctica, which is wonderful, but there's one problem. I told you that to know where the float is, it needs to talk to the satellite. If it's coming up under the ice shelf and banging its head on the ice shelf repeatedly, it doesn't know where it is. We don't know where it is. So we had to do some detective work. We know actually how far the ice shelf extends into the water very accurately from satellite measurements. They can measure the thickness above the water, and from that infer how deep below the sea level the ice must extend. That's called the draft of the ice shelf. Every time the float ran into the base of the ice shelf, it provided a measurement of the draft of the ice shelf, and we could match up those two and constrain where the float had likely been underneath the ice shelf. And it told us a lot of things. The two main messages is that the Denman Glacier is vulnerable in the sense that warm water is flowing into the cavity beneath the Denman Glacier. Whereas the much larger Shackleton ice shelf is apparently stable because only cold water is reaching below the Shackleton ice shelf at the present time. So the plot on the left shows a map. The orange arrow labeled 1 is where the warm water is flowing in under the Denman Glacier, and the blue arrow labeled number 3 is meltwater coming out of that cavity. And so we can tell those two things are happening by the measurements that the float has made. The yellow line shows the trajectory of the float, and the plot on the right is a vertical section along that transect. So this is a long transect under the 2 parts of the ice shelf, as well as the surrounding water. The orangey color in that plot is warm water, and there's meltwater coming out at shallower depths beneath what's labeled as the Denman Northcliffe ice tongue there. Beneath the Shackleton, the water looks pretty boring. It's all blue. That's all cold water. So that's why I said that the Denman is apparently vulnerable while the Shackleton is stable. If we'd had a choice, we might have preferred it the other way around, because the Denman actually provides much more buttressing and is a stronger outflow of ice from the Antarctic continent than the Shackleton is. But it is what it is. The Denman's vulnerable and the Shackleton is stable in today's conditions. The black shape on the right-hand plot shows the bottom depth as measured by the float. And you can see there's very deep canyons, more than 1,000 meters deep, measured underneath the Shackleton ice shelf. The dashed white line is where we thought the seafloor depth was before the float made these measurements. They're 500 to 1,000 meters different. The significance of those deep channels under the Shackleton is that if warm water does get to this part of the continental shelf, there's a channel that would allow that warm water to penetrate far under the ice shelf. I showed the plot on the right here before, showing how a bump on the seafloor regulates the amount, just how much warm water reaches the ice shelf. And we've measured that at some of these East Antarctic ice shelves. The plots on the left show temperature as a function of depth as you go down through the water column, taken in different years. And the numbers at the bottom are the temperature at the seafloor, the warmest water that was present. And you can see in those profiles, there's cold water at the surface and warm water below. The thicker that warm water layer is, the more higher it extends off the seafloor, the warmer the water that reaches the ice shelf. And the reason is because that warm water finds it easier to get over that intervening bathymetry that's regulating how much heat reaches the ice shelf. Knowing that is important for assessing the vulnerability of ice shelves in the future, because what we really need to know is what's regulating the thickness of that warm layer and therefore its ability to access the ice shelf cavity. So to sum up, there are a few messages from this float. One is that it's good to get lucky now and then. The second is that some East Antarctic ice shelves, in particular the Denman, but we've shown similar things from the Totten. Those two systems that Paul mentioned as having retreated by an amount that's pretty similar to some of the West Antarctic ice shelves, that warm water does reach those systems, so they're potentially vulnerable and at play in terms of their contribution to sea level rise. The kinds of sea level rise curves that you've seen people show imply that we will need to do something about this problem. We will need to adapt. So, for example, a famous study from 2013 written by Stefan Halagata, who was an economist at the World Bank, looked at just the 136 largest coastal cities and found that by 2050, if we don't adapt, losses due to coastal flooding will be in excess of $1 trillion a year, every year, and growing. More recent studies suggest that if anything, that study was conservative, that the losses are higher. By 2100, with 86 centimeters of sea level rise, so not a number that involves any instability of the ice sheet, but under a scenario kind of similar to continuing to operate as we are today, that number is something like $14 trillion a year. Chances are we won't let that happen. We will adapt where we can, and adapt means build dikes, build seawalls, rely on accommodating the extra water through the way we deal with floodwater in urban environments or wetlands to act as a sponge, or relocating from places that we can't defend. All of those adaptation exercises, although necessary, are hard, expensive, and we really need to be guided by the best possible information. So the policy relevance of this kind of work is really that we have some tough decisions to make. And to make those decisions, we need the best possible information we can get about just how vulnerable the Antarctic ice sheet is, and therefore how much and how fast sea levels will rise. Thank you.